Dear friends, in previous class we discussed about Chinese remainder theorem. What is Chinese remainder theorem? If M1, M2, etc. Mr are relatively prime in pairs, then the system of congruence x congruence to A1, x congruence to B1 mod M1, etc. x congruence to BR mod M1 has exactly one solution modulo the product M1 etc. M1, and that solution is x equals B1 M1 M1 dash plus B2 M2 M2 dash plus etc. plus BR MR MR dash. Then now let us discuss another result. So the result says that let F the result says that if M1 etc. M1 etc. M are relatively prime in pairs, B1 etc. BR are arbitrary integers, and let A1 etc. AR satisfies, AK and MK are relatively prime in pairs, then the linear system of congruences A1x congruence B1 mod M1 etc. ARX congruence BR mod MR, ARX congruence BR mod MR, BR mod MR has exactly one solution modulo M1 etc. MR. So the theorem heavily depends upon Chinese remainder theorem. So its proof is, since AK and MK are relatively primes, AK is given, AK and MK are relatively prime pairs, then there exists a unique solution AK dash, which is called the reciprocal of AK for the congruence AKX congruence to 1 mod MK. Since AK and MK are relatively prime, there exists AK dash, which is called the reciprocal of AK for the congruence AKX congruence to 1 mod MK. That means AKX congruence, then we have AKX congruence to A1x congruence to B1 mod M1 etc. Therefore AKX congruence to BK mod MK, AKX congruence to BK mod MK, it is already given, where K equals 1, 2 etc. up to R. So that means AK dash X congruence to BK AK dash mod MK, since AK and BK are relatively prime in pairs. So that means, what is X here? AK dash is the reciprocal of AK, so X congruence to AK dash BK mod MK. Since, but Mi and Mj, so mark this equation 1, but Mi and Mj are relatively prime in pairs. Therefore, this system X congruence to AK dash BK mod MK, where K ranges from 1 to R, has unique solution modulo M1 etc. MR. Why? Because of Chinese remainder theorem. Therefore, A1x congruence to B1 mod M1, A2x congruence to B2 mod M2, etc. ARX congruence to BR mod MR has unique solution modulo M1 M2 etc. M1. Okay, AK and MK are relatively prime, therefore there exists AK dash, which is nothing but the reciprocal of AK modulo M, or AK for the congruence AKX congruence to 1 mod MK. But we have AKX congruence to BK mod MK, that's already given here, A1x congruence to B1 mod M1 etc. and so on. Here K ranges from 1 to 1. Then clearly AK dash X congruence to AK dash BK mod MK, ak dash be the reciprocal of ak means x congruence to ak dash bk mod mk. That means yes, but mi and mg are relatively prime means therefore the system x congruence to ak dash bk mod mk has exactly unique solution modulo m1 m2 etc m1 because from Chinese remainder theorem. Therefore a1x congruence to b1 mod m1 etc arx congruence to br mod mr has unique solution modulo the products m1 m2 etc m1. Okay. So the this theorem heavily depends upon Chinese remainder theorem. Then, by using the arguments of Chinese remainder theorem, find all x which simultaneously satisfies the system of congruence x congruence to 1 mod 3, x congruence to 2 mod 4, x congruence to 3 mod 5. Solve the system of congruences. Find x which simultaneously satisfies these three congruence relations: x congruence to 1 mod 3, x congruence to 2 mod 4, and x congruence to 3 mod 5. Here, this problem is solved by using Chinese remainder theorem. Here, what is m? What is m actually? M is the product of this modulus. What is the modulus? Here, the modulus m1 equals 3, m2 equals 4, and m3 equals 5. So these are the modulus. So what about the m product to m? M is the product of this modulus, that is 3 into 4 into 5. 3 into 4 into 5 means it is 60. Then x congruence to 1 mod. So what is you can choose mk. What is mk? Mk equals m by small mk. Thus this small mk and capital Mk are relatively prime. That means, so what is here m1? M1 equals m by m1. M by m1 means 20. 4 into 5 by 3. And what is m2? Capital M2. M2 equals capital M by small m2. Capital M means 3 into 4 into 5 by small m to 4. So it is 15. Similarly, capital M3. M3 equals 12. Okay. Yes. Now, clearly this mk and mk are relatively primes, means m1 and capital M1 are relatively prime. Okay, what is m1? 3 and 20 are relatively prime, 4 and 15 are relatively primes, and 5 and 12 are also relatively primes. M1 and M1 are relatively prime, M2 and capital M2 are relatively prime, small m3 and capital M3 are relatively prime. Now, we solve the relation mkx congruence to, to 1 mod mk, where 1 mod mk, here k equals 1, 2 and 3. Okay, but we have the solution of ax congruence to b mod m. What is the solution of ax congruence to b mod m? We also prove that the solution of ax congruence to b mod m means, or the congruence relation x congruence to b mod m has unique solution whenever a and m are relatively prime, and the solution is given by x equals b a power 5m minus 1 mod m. Okay, x congruence to x congruence to b mod m has unique solution only if a and m are relatively prime, and that solution is given by b into a power 5m minus 1 mod m. So according to that argument, when k equals 1, we have m1x congruence to 1 mod, what is small mk? Small mk is small m1 is 3. Okay, so it is m1x congruence to 1 mod 3. What is m1? M1 is 20. So the first relation is m1x congruence to, consider the first relation, For solution, m1x congruence to 1 mod m1. Not for solution, first congruence relation. m1x congruence to 1 mod m1. What is m1? Capital M1 is 20, means 20x congruence to 1 mod. What is small m1? It is 3. So this 20x congruence to 1 mod 3. Clearly, a and m are relatively prime. 20 and 3 are relatively primes. Since 20 and 3 are relatively primes, therefore it has a solution x congruence to b into a power 5m minus 1. What is b? b is 1. So it is 1 into, what is a? A is 20. When you compare, so it is a is 20, so it is 1 into 20 power 5 of m. Here it is 5 of m1. What is 5 of m1? 5 of 3. Means 5 of 3 minus 1 mod 3. That means x congruence to 20 power 5 of 3. What is 5 of 3? The numbers which are relatively less than or equal to 3, less than 3 are relatively primes to 3. Okay, so it is 1 and 2, so 5 of 3 is 2, 2 minus 1, 1, so it is x congruence to 20 mod 3. X congruence to 20 mod 3 means x congruence to 2 mod 3. Okay, 20 mod 3, if you divide 20 by 3, the remainder is 2, hence x congruence to 2 mod 3, that means here m1 dash equals 2. b1 m1 dash. m1 dash equals 2. Agree? Now consider the second result. So the congruence relation m2x congruence to 1 mod m2. What is capital M2 here? Capital M2 is 15. So 15x congruence to 1 mod small m2, that is 4. Since 15 and 4 are relatively primes, therefore there exists a unique solution. It is given by x congruence to this one, b into, what is b? Compare, it is 1. And what is a? A means it is m2, that is 15. So it is 15 power 5 of m2, means 5 4 minus 1 mod 4. Agreed? So that implies x congruence to, what is 5 of 4? 1 and 3 means 2. 2 minus 1, 1. So it is x congruence to 15 mod 4. Congruence 15 mod 4 means x congruence to, if you divide on 15 by 4, so it is the remainder is 3. So it is x congruence to 3 mod 4. That means what is m2 dash? m2 dash equals 3. Okay. So m1 dash equals 2, m2 dash equals 3. Similarly, you can solve the third linear congruences. Here it is, we already obtained m1 dash equals 2, m2 dash equals 3. Come to the third one, that is m3x. m3x congruence to 1 mod small m3. That means, what is m3x? m3 means 12, so it is 12x congruence to 1 mod 5. Since 12 and 55 are relatively primes each other, therefore there exists a unique solution. X congruence to b means 1, a means 12, so it is 12 power 5 of 5 minus 1 mod 5. That means x congruence to, what is 5 of 5? P is a prime number, 5 of p is p minus 1, so it is 4 minus 1, that is 3, means 12 cube mod 5. What is 12 cube? 12 cube is nothing but 1728. That means x congruence to 1728 mod 5. If you divide 1728 by 5, surely the remainder is 3 itself. So that means x congruence to 3 mod 5. So that means m3 dash equals 5. Sorry, m3 dash equals 3. So there are 3 values, m1 dash, m2 dash and m3 dash. So you have m3 dash equals 3. So it is a solution, hence the solution is x congruence to b1 m1 dash, b2 m2 dash. So the solution is x equals or x congruence to b1 m1 dash plus b2 m2 dash plus b3 m3 dash mod capital M. That means x congruence to b1, b2, b3 are arbitrary integers. Here it is 1, And what is m1? 20 and m1 dash. So it is 20 into 2 plus b2 1. What is m2? m2 is 15. So it is 15 into 3 plus b3 is again 1 and m3. What is m3? 12 into m3 dash is 3 mod m means 120. So that means x complements 2 into 20 plus 31, so it is 238 mod 120. So x complements 2, sorry, not this 120, what is capital M? Capital M is 60 only, sorry. So it is yes, x complements to 238 mod 60. That means x complements to, if you divide 238 by 60, then the remainder is 58. So it is 58 mod 60. So the system has unique solution, means the linear congruences x congruence to 1 mod 3, x congruence to 2 mod 4 and x congruence to 3 mod 5 are simultaneously satisfy this relation. So it has a solution x congruence to 58 mod 60. So this is the required unique solution. Okay. Now we consider another result. There is application of Chinese remainder theorem. So the theorem states that let f be a polynomial with integer coefficients m1, m2, etc. m are be the positive integers m1, m2, etc. m are the positive integers, m3, etc. m are be the positive integers. They are relatively prime in pairs, means mi, mj are relatively prime in pairs, means GCD of mi and mj is 1 for all I differs from j. And consider the product. Let m is the product of this mi's. That is m equals m1 etc. m. Then the congruence f of x congruence to 0 mod m. Then consider the relation f of x congruence to 0 mod m has a solution if and only if each of the congruences f of x congruence to 0 mod mi has a solution. F of x congruence to 0 mod m has a solution if and only if each of the congruence f of x congruence to 0 mod mi has a solution. If and only if relation. Moreover, if v of m and v of mi denote the number of solutions, then v of m equals v of m1 into etc. into v of mr. How to prove this one? So the proof is according to Chinese remainder theorem. So yes, this is nothing but an application of Chinese remainder theorem. So the proof is, if A be the solution, of f of x congruence to, first suppose that f of x congruence to 0 mod m has a solution. If A be the solution of the given relation or the congruence f of x congruence to 0 mod m, so that means f of A congruence to 0 mod m. Okay, f of A congruence to 0 mod m. F of A congruence to 0 mod m means m must divide f of A. Sure. What is m? M means the product m1 etc. mr. mr must divide f of A. mr must divide f of A means each of this mi must divide f of A. Since each of these mi, mr are relatively prime, or mi, mj are relatively prime in pairs. So mi for all I differs from j. So mi divides f of A means f of A congruence to 0 mod mi. That means A be the solution. That means A be the solution of the congruence f of x congruence to 0 mod mi. So the first part is finished. Okay, right. What about the reverse inclusion? So for reverse inclusion, if f of x congruence to 0 mod mi has a solution, then f of x congruence to 0 mod m also has solution. So let A be the solution of for the reverse inclusion, let A be the solution of f of x congruence to 0 mod mi. If A be the solution of f of x congruence to 0 mod mi, then we have f of A congruence to 0 mod mi. Okay, f of A congruence to 0 mod mi. But what about m1 etc. mr? It is given m1 etc. mr are relatively prime pairs. So you can apply Chinese remainder theorem here. So according to Chinese remainder theorem, there exists an integer a such that x congruence to ai mod mi has a unique solution. Therefore, since there exists an integer a such that x congruence to ai mod mi has a solution, that means a congruence to ai mod mi. If a be the solution of this one, by Chinese remainder theorem there exists a solution to this congruence, let it be a, then a congruence to ai mod mi. What is f? But f is a polynomial with integer coefficients. Therefore, if a congruence to ai mod mi, then f of a congruence to f of ai mod mi. Why? Because if a congruence to b mod m and f is a polynomial with integer coefficient, then f of a congruence to f of b mod m. The result is already proved. But what is f of a? Given f of a congruence to 0 mod mi, therefore f of a congruence to 0 mod mi. F of a congruence to 0 mod mi because f of ai is given. We have f of a congruence to 0 mod mi. So f of a congruence to 0 mod mi. F of a congruence to 0 mod mi means it is f of a congruence to 0 mod m. Why? Because m is the product of all of these mi's, means this mi and m are relatively prime. Therefore, f of x congruence to 0 mod m has a solution. So this is the reversing question. Okay, and its remaining part, that is so immediate, so it is left as an exercise to you. Then so try it yourself. The second part is try